тема моего доклада, презентации. Проблема в том, что я его готовил на английском, и, в общем-то, я буду говорить на английском. Но если у вас будут проблемы с тем, чтобы понять какие-то вопросы, вы можете мне перебивать в значимых местах и спрашивать. Окей? Договорились? Хорошо. So, monads are just monoids in the category of endofunctors. This is the title, and this is me, Ike. I'm team lead at TopTal. Probably most of you hear of it. This is my contacts, so if you have questions and you will need some more deeper explanation of the stuff, reach out. I'll try to help you. And let's go to the next. So, monads are just monoids in the category of endofunctors. This is very, very precise and very concrete explanation of what monads are. But to understand this stuff, you have to know what monoids are, what category are, what endofunctors, and how all this stuff connected together. What this whole thing means. So I will try to give you this understanding, going by bit by monoids, then category, endofunctors, and these two together as category of endofunctors, one thing. So, and we will start with the very, very basic. We will start with this. We will actually change the perception on the function definition below and the way we write them. This part, this slide, is actually for, not the guys who work with functional languages. So I suppose with you it will be easier. But anyways, so this is the type of the functions. And for example, for functional length that takes string and returns the length of the function as number, this is the way we define it in something like Java, C#, whatever you prefer. And the application of the function will almost always look like this. So forget about this stuff. This is the way we will use it. This is the way we will write it. So instead of having this column, we will have arrow between objects, between the types of the strings and numbers, for example. And say that the length function is a transformation from string to number. And arrow is actually represents this transformation. Application of the function is almost the same without parentheses, and we avoid this stuff in order to have less mess in the code, less mess in the way we write this stuff. So it will be easier for you to understand and to read. Yes. So I think this is okay. We are good with this, and let's go with the. What's going on? Okay. Something is not working. How to sorry about this. I don't know how to make this work. Okay. Yes. So I will start with category. Category is the very, very basic element of the whole category theory. It forms the category theory, it explains the category theory, and in fact, if you think of this thingy of the category, it actually explains every structured elements that you have in the math, in the computer science, in anything. It defines what is the structure of anything. And if you get the category, it's very easy. If you get the category, you will be able to comprehend the whole variety of stuff from, in depth. Not looking at the higher level, let's call it API, higher level things, but to understand the root of the stuff. It's very important and it's very helpful in your day-to-day work. This is the definition of the category. So category is a bunch of objects with added arrows connected by composable arrows. I would stop here, but this thing has to be explained better because I know this sentence is very short and some may already see the pattern, but anyways, let's go deep. Let's understand what objects are, what arrows mean, and what the hell composition, composable stuff, and identity has to do with this. So, again, what the hell? Okay, this is the slide. So what we will do, we will define a bunch of functions. You probably all kind of know these functions, use them, or wrote on your own. So our first one is very simple function that takes Boolean and returns Boolean. It actually, if you give true, it will return false, false will return true, this kind of stuff. Second, we will add 5 to any number you give, and it will return also 5. Result is the same kind of function that will say if the number you gave to it is actually a bool or is actually odd or even. It's very simple. Length we already saw, and lower it will just lowercase the string. Okay, so how this will map to category? This doesn't help. This definition of the functions doesn't help. But if you try to map this to diagram, like this one, we will see the actual arrows. So the arrows we had here, this one, will transform to I don't know how to make this thing here. Will transform to arrows here. So we had to learn that was taking string and returning string. So it's actually, if you map each type we had as dots, string, number, boolean, they will go from this dot back to the same dot. And functions that take string and return number will form this arrow that goes from this dot to this dot. And from number to boolean, as you can see, rest is actually the same. And this is a category. This is a category of types. The very basic element of computer science. This is the thing that you use on day-to-day basis. And this is the thing, if you get, you will be able to comprehend the computer science and essentially what you do every day, how you program it, how this all stuff works. So, bunch of objects, right? Bunch of objects in this case is actually these dots, string, number, boolean. So each dot is actually the object. And these arrows are the arrows that go from these objects to the same object. So to lower, there might be actually to uppercase. It will have the same type. It will go from string to string. And composable arrows. Actually, all arrows here are composable. So this is the category. In category, we don't care about the actual stuff. So, in the string dot, inside of the string type, there is infinite number of strings. There might be a lot of strings, right? There's infinite number of them. And we don't care about this stuff. If we go one level up, if we go to talk about the types of the stuff, not the actual things. And we actually need these types, we need these objects in the category theory just to have a place to attach our arrows. So that's objects here just to have start for arrow and end for arrows. And category is essentially about these arrows and how they interact with each other and how they can be composed. So, we don't talk about actual strings or actual numbers, actual Boolean values, or any actual values that have to be, if we have. We care about only the types. And this is why it's called a category of types. It's again Hello? Give me one second.
Accessibility options.
Okay. Now it's better. Now in color. So the same stuff. This if we add to the definition of the category I had before 2 new elements, we actually will get the whole category theory as one thing, and we will get the root that will help us to understand monads, endofunctors, functors, and essentially the monads. So what we have to do, we have to talk about the composition of functions. This is very, very easy for you because you already know that, because you do it every day, and because it is the way to write programs. You can't write anything if you can't compose functions, because in that way, if you avoid composition, you will essentially write assembly something, right? So this is the thing we have to do. We have to define composition. And category theory and category thinking, the category theory defines the composition. It says that between, if there is arrow between string, for example, between 2 objects, and arrow between the second object and third object, for example, in our case, string number and number boolean, we automatically get new function that will be composition of these 2 arrows. New arrow that will go straight from string to number. And this new thingy this new function is the same type of the function as other functions. You can compose it further with other stuff, and it will work because it's just regular arrow now. It's just one more function that you get automatically from the definition of other functions. So the type of it, the way to think of it might be this, right? So length after is odd will be morphed to this, Java-ish version that will look like this. I don't really think you have to. I have to explain this to you, but the essential part is that we don't have here number. So string directly to boolean, the arrow between these 2 objects. There is no intermediate object between these 2 stuff. There is no boolean, and this new thing is actually a new function, just right there. So this is the composition, first part of the composition. Second part is that in the composition, when you compose functions, arrows that go from one object to a second object, and these identity arrows like to lower, the composition of identity arrows with other arrows will give with the same type. So if you had to lower and length, like in this example, and you compose them, the type won't change. The to lower length is actually string number, and length is string number. So identity arrows composed with anything else will give the same stuff back. And this actually helps to map the whole category theory with monads and with monoids. But let's not get ahead of it. So to give you an example of this, if you have a string and you lowercase it and then take a length, if you take length of the string right away, you will get the same length. You will get the same number. It won't change if it's lowercase or uppercase, because the number of elements, number of characters in the string will be the same. So this is one way to look at it. But don't go deep in the details about the actual strings on this. Care about types. So we care about that type is the same. And in category of types, if type is the same, it actually means that these arrows are interchangeable. So to lower length and length, they can be used in the same way. They can be used in the composition in one way or another way. So when you have composition of this thing or this thing, you can actually swap them just like that, because they have the same type, and that won't bring the category of types. So if we try to go back, okay. If we try to generalize that stuff, we will get this as general category. So I was talking about category of types. Category of types is the thing that we care about, but category is bigger thing. It's much bigger actually. You can have category of categories. So it's like meta-category. Think about categories that it can form and can mean anything to express any structure, and arrows don't actually have to be functions. They actually might be other ways of transformation and other ways to connect things. So the general view of the category will look like this, and with these two functions, with these two rules of the category. So there is a composition if there is error between two objects, or three objects, right? And the composition with identity errors like 1A won't change anything, won't change the type. So yes, this is the category. If you have questions here on the category, speak up. No? Okay. Second part. So we have this monads are just monoids in the category of endofunctors. We know category now, more or less, and we have to understand endofunctors and monoids. So let's go with endofunctors first, and then we will try to go with monoids. Endofunctors are easy. Well, yes, they're easy. So endofunctors definition, in simple words, will be this: structure preserving transformation from a category back to the same category. If you try to look at it as a diagram, it will look like this. So we have the whole category of types as a dot here, right? Any category, in fact, is a dot. And endofunctor is just arrow transformation, another arrow that goes from the same category back to the same category. And in our case, in case of category of types, we actually have very good endofunctor that we can talk about. So we will take maybe endofunctor as an example and try to look at it as a thing. So dot here is the category of types, the thing that we saw before, and maybe is just transformation of the category of types. And what it does, it takes any objects, right? We have this dot string, number, boolean, so it takes any objects, wraps it inside of new type. It might be, this is it, just string or just number, or it will say that there is nothing. Essentially, you can think of endofunctors as boxes. So you take actual objects and put them inside of the box and start to care about the box and work with the box and care around the box. What they actually give as second level of how they might be applicable and how they're actually useful is that they allow you to apply the functions that work with regular objects inside of the box. So we have this length function for the string that will return a number, right? Say that the length of the string is like 5 or something. And you can actually apply that inside of the box. So maybe endofunctor has a way to apply the function inside of the box if there is a string inside of the box. And this is actually very helpful when you try to build a system that will be fault tolerant. So you can change functions that will work with maybes, with chain of maybes, and they will be applied to the actual stuff inside of the box only if there's actual thing inside of the box. So one of the ways to define this will be to actually check if thing inside of the box in this just something is string, or you can use pattern matching, which is much preferable, right? And then apply the function. This example is fictional. There is no language that will allow this syntax, but this is like to give an example. So yes, this is the endofunctor. Box is a way to apply functions inside of the box. And if you apply the maybe endofunctor to the category that we knew, that we saw before, the category of types, we will get the map of that category, new part of this category. So there is mapped version, maybe version of each object. So we have string, numbers, boolean, we got maybe strings, maybe number, and maybe booleans. And since maybe endofunctors gives a way to apply functions, we know we have the same arrows, and this is essentially why it's structure preserved. If structure in the category is the arrows, and if we preserve the arrows, then we actually preserve the structure. So this The whole thing now is a category of types. Since endofunctors don't create new categories, they change categories in place, we got the new extended version of the category of types, which allows us to do much more things. We now have a very safe way to define division by zero, for example. If you try to divide by zero, you will get none, right? In most of the cases, nil, null, none, or something like this. Sorry. And now with maybe, we can actually say nothing, and like this operation is not defined. And we get safer programs, safer way to write applications. So yes, this is the endofunctor. Do you have questions on this?
So functions works only with category of maybe. Yeah, it waits for example, to lower it. It waits for maybe string and it returns. Короче, функция to lower, она ждет maybe, правильно? То есть она возвращает maybe, ждет maybe, возвращает maybe.
Она работает внутри maybe.
А то как дать значение и ожидать, что она либо даст результат, либо ничего не даст.
Да. Поскольку мы... Окей, я буду использовать английские слова, где не могу найти в русских. Поскольку мы будем применять функцию внутри maybe, сама maybe может нам сказать, если получилось или что-то или нет. Если не получилось, она вернет nothing, и этот nothing будет на самом деле частью maybe. Это будет уже этот тип новый. Но функция сама to lower, это та же самая функция.
Та же самая.
Просто мы нашли способ сделать так, чтобы она работала с maybe, с этой коробкой. На самом деле коробок намного больше. Есть maybe, есть other, есть error monad, есть state monad. И они все работают.
То есть endofunctor это maybe string, правильно?
Да, это будет maybe, это один из endofunctorов. А maybe string это...
Это более высокая абстракция получается, на string.
Да.
В случае с категориями мы точно знали, что функция нам вернет, а в случае с endofunctionом мы определяем, что нам либо один результат, либо второй результат.
Поскольку в коробку можно положить что угодно, любой тайп, она полиморфична по типу. То есть функции, которые работали со стрингом, они будут работать только с maybe string. Но сама maybe полиморфична. То есть мы можем туда положить любой тип. И только те функции, которые с этим типом работали, будут продолжать работать только уже в этой коробке. И это на самом деле позволяет строить очень большие и при этом очень безопасные системы, в которых мы продолжаем работать с теми же функциями, с чистыми функциями, но при этом мы можем давать больше гарантий и обрабатывать больше ошибок. Допустим, если попытались поделить на 0. В обычном случае мы можем вернуть none, и тогда функция станет от двух типов. Она будет полиморфичной, number или же none, если мы определим как свой тип. А тут мы можем говорить точно, что ошибка. И это будет безопаснее и, в общем-то, проще поддерживать.
Интересно, а есть какая-нибудь вот тулза, которая построит вот такие красивые отношения функций с вот такими замечательными транзитивными замыканиями прямо вот из моего кода?
Нет.
Ну так, просто интересно.
Если ты мне заплатишь денег, это будет дорого. Очень.
Выглядит для презентации заказчику. Людям будет нравиться. Хоть они ничего не будут в этом понимать, потому что очень технично.
Я могу выделить вот все эти штуки, которые использовал в своей презентации, как библиотеку к Sketch. Их можно будет использовать дальше. Но это отдельный разговор. Okay. So, okay. Monoid. Category, endofunctor, monoid. If you understand monoid, it actually will be there. It's like the finish line. So, monoids defined not in the category theory, They're actually part of different branch of mod. But there is a way to talk about monoids in the category theory. And since we work with the category theory, since we know a bit now more about the categories, we can talk about monoids in the category. And I will try to show them to you as simple as possible. So the definition of monoid will look like this. It's a set of elements, it's not bunch now, it's set of elements with a unit element and a binary operation for combining these elements. If we try to simplify this or go a bit deeper, we will get this stuff. So set S is elements A, B, C, unit element E, binary operation orange dot on this set is a monoid only if these two laws can be applied. So this first says that if you combine AB and then result of AB with C using this binary operation, or A with result of BC, they should give you the same stuff back. This is the first law. Second law is easier. It doesn't matter how you combine this unit element, you will still get the original element. So A combined with E, which is unit, will always be A, and E with A will always be A. As you can see, we didn't say about that. We say that there is actually the combination from left and from right. It's not important. We don't care about these technicalities. But the essence of the monoid is here. We can go a bit more, abstract and define some kind of types for this operation for orange dot and for E. We will use this letter, so try to remember them. Actually, don't. There is a slide for them. But anyways, orange dot on type on monoid S will look like multiplication of S's that will return this error, right? The set element of the set. So we can't go beyond the set. We still work in the set. We just found a way to combine two elements of the set to get two other elements of the set. This element, the result element, is still there. It was there from the very beginning. We just found a way to get to this to this element of the set by combining the other elements of the set. This dot operation, binary operation, sometimes called multiplication, because because this operation of elements of the set, it's like combine two elements of the set, or combine set, you get new set. So you can think of multiplication of elements of the set. Multiplication not in the terms of multiplication of numbers, but as general multiplication, general thing. And for E, it's actually one of the combinators, but anyways, it's a thing that will return always element of the set, the unit element of the set. If you try to look at it as a function, it will be a very simple function that won't change, won't have any complex definitions. So this is not helpful, I know. This is helpful. So strings actually monoids. If we take string and concatenation as a binary operation, these two things together will form one of the very basic monoids. So unit element is empty string, and no matter how we concatenate any string with empty string, we will get the original string. So Ruby concatenates with empty string, any number of empty strings will always give Ruby, right? And second part is about the order of combination. So if we combine bunny with love and then with carrot, we will still get the same as if we combine love with carrot and then reprint with bunny. So this thing is one of the very basic monoids. There are actually much more monoids that you know. For example, numbers with multiplication and number 1 is actually a monoid, because no matter how you multiply by 1, you will get the same stuff, and the order of combination does not. Same with numbers, addition, and 0. It will also form a monoid, one of the basics. And there is actually much more if you start to look deeper in the stuff. But yes, this is the essence of the monads.
Так как композиция функций в контексте моноида, она имеет коммутативность только с единичной функцией, ну, с универсальным таким множеством, или между собой тоже? У вас там было вот там, А композиция Е равно А равно Е композиция А. Да, вот коммутативность получается. Да.
Мы ее не определяем. Мы забыли про нее. Мы не паримся про нее. Мы не определяем коммутативность. Как раз тут мы говорим, что ее нет. Мы говорим, что мы про нее не беспокоимся, потому что мы определили две разные операции. Слева и справа.
А вот если вместо единичной функции, ну я не знаю, как ее буду называть, или, например, какая-нибудь b, мы можем сказать, что А композиция b равно b композиция А?
Нет. Коммутативность в моноиде не определена.
Ага, то есть коммутативность только с единичной такой вот функцией?
Нет, она не определена. Она здесь тоже не определена. Мы говорим композиция с единичным элементом слева, композиция с единичным элементом справа. И они могут быть разными. Но с единичным элементом они всегда дают А. Потому что неважно, вот эта вот композиция с единичным элементом, только это мы знаем. Тут не так, что типа мы определили ее, это просто типа выходит из того, что у нас есть единичный элемент. Вот. Так. Okay. Do you have more questions on the monad? Есть еще вопрос по монадам?
Надо какое-то практическое рассмотрение.
Так. Вот это даже практично. С Руби, кроликами.
Как-то... Как его нужно использовать, например?
Моноиды сами по себе. Моноиды сами по себе использовать можно только как часть большего, как часть endofunctor, допустим.
Для решения задач про моноиды?
Нет, для решения того, как типа получить монаду, как вообще определить монаду. Окей. Все это вместе. So, there is monoids, there is category, there is endofunctors. In the original definition, we had monads are just monoids in the category of endofunctors. So we have to define what category of endofunctors will mean, and how to, the second part is actually how to inject monads in the category of endofunctors. Let's start with the simple stuff. This category of endofunctors. Hopefully. Okay. So, we have this maybe endofunctor, right? There is more endofunctors that you know, probably. So there is list endofunctor, there is I endofunctor, ID endofunctor, and if you remember the original definition, right? The original diagram, there is a category of types and there is endofunctors. And it's not very visible here, but there's just arrows like this one, and there's much more. They all extend the category of types. They all operate on the category of types. And they form category themselves, these endofunctors together. If you look at this diagram from different perspectives, yes, it will look like this. And this thing together is actually now endofunctors on the category of types and category of endofunctors. And we have the arrows that go between the endofunctors, the morphism on the endofunctors. Like we have to list that will take identity endofunctor result, right, and form a list from this. Or we have a function, this new transformation from the list to maybe element of the list. And these new arrows, they can't be seen in the original category of types. They exist in the category of endofunctors. And yes, so let's talk about the actual endofunctors here. So ID is a box that will always have something inside of it. It's a very simple box. It's like if there's a box, there's actually value inside of the box. So ID string will always contain string, and application of the length inside of this box will be very easy. Right? List is a bit more cumbersome. So we have list that takes string, right? It actually forms some kind of array-ish stuff. It's actually array. In most of the languages, array is actually list of the factor. So it's always actually list of the factor. Anyways, array, and to actually apply the length inside of the array, we have to do a lot of thinking, because array might be empty, and if you try to get length of empty element, of empty stuff, we will get error. We don't want that. Our array might be of multiple elements, right? And we have to think of it and define of each element of this array we want to get length. So one way will be to get on the first element. But still, we have this probability that array will be empty and head will return nothing, or it will fail if it happens. So we can define this new arrow from list to maybe. It will take list endofunctor and return maybe endofunctor. This is very new thing. It's not like the functions we saw before, because its types, the type on the left and type on the right, are actually endofunctors. This is a transformation of endofunctors, and this is why it's category of endofunctors. So okay, head will look inside of the string, inside of the array, but very much if there's a x, right, the first element, if it is there, then it will return that actual stuff. If there is nothing, then it will return nothing from the maybe. So head will have this new type. Yes. And length with this stuff applied will look like this. So from the list of strings, from endofunctor on strings to another functor on different type of number. And this thing is called actually, it has name, it has title. This transformation, this type of transformation is called natural transformation. It's one of the very basic concepts. But we don't have to get this stuff from, on this level. But you have to understand that there are functions that operate between endofunctors. There's arrows that take one type of endofunctor, might return another type of endofunctor, and there's actually a lot of them. And we can compose them, we can get new stuff, and because, for example, if we had another function that from maybe number to something else, we could compose this new length with that stuff. So this is the composition of functions that operate on endofunctors. And these things are from the category of themselves, category of endofunctors. So nothing very complicated. Do you have questions on this stuff?
Я правильно понимаю, то есть получается категория это мы задаем алгебру множеств из как бы наших этих контекстов, в которые завернуты уже непосредственно string, number, то есть мы задаем саму алгебру множеств и операция над контекстами, а контексты у нас являются эндофункторами, title контекст.
Категория это только про то, как можно объединить все эти штуки вместе, как получить композицию. Как получить композицию где угодно?
Так я об этом и говорю, то есть это получается, называется алгебра множеств и операция над ней. По сути вот так.
Надо чуть проще и чуть точнее. Если чуть точнее,
не получается.
Чуть точнее это только то, что есть композиция. Если ты говоришь, что это что категория, и она соблюдает вот эти вот категоричные законы, то ты получаешь композицию. Все, ни больше, ни меньше. Это все, что есть про категорию, это все, что важно про категорию.
Получается, у нее одна операция, это композиция.
Да. И две интерпретации. Композиция с identity и композиция с любым остальным. Okay. Monoid in the category of endofunctors. What does it mean? So we have monoids. Monads are just monoids in the category of endofunctors. We know monoid, we know category, we know endofunctors, and we even have some understanding of category of endofunctors together. So what is left to somehow find monoid inside of the category of endofunctors. If you do that, actually you will find monads. But it's a bit complex. We can't really find the monoid, but we can inject monoid inside the category of endofunctors. We can add something to the category of endofunctors that will extend the category of endofunctors in the new way, that this sentence, monoid in the category of endofunctors, will actually have meaning. So to do that, let's go back and see what is operations on the monads that we saw. The types of binary operation, right? This is the type, and type of this unit element. I have to say that these types, not types per se as functions, as of types of functions, but type of operations. So they're a bit different. This is why we have this multiplication sign here. So yes, this is like general understanding of the type, not actual type of the strings or numbers, transformation of this stuff. So, okay. How we can inject this stuff inside of the category of endofunctors? Okay. Well, I have an answer. And it is like this. Let's take very simple endofunctor list that transforms, that has this array thingy, right? It will return you something of type array. And define somehow binary operation on that stuff. So element of this set multiplied, or you can think of this as s squared to return s. How we can define some function, actual function, in the category of endofunctors that will have some similar type. And for strings, or for list of strings, it will be easy. For list of strings, there is a way to do that. You can see this type has the string of arrays inside of arrays that will return string of arrays. It like string in squared arrays or something like this that will return just regular array of strings. And the operation join, function join, in most of the languages it's called flatten or flat, something like this. It doesn't matter how exactly, but there is a resemblance between the types here and types here. As you can see, we had s multiplied by s that will return s, set will return s. This is the same stuff, but from category of endofunctors. So strings squared will return array of strings. The second part is much easier. This is a return function that will take string and just put inside of the singleton list, singleton array. So array that will have only that element as inside of the as first element, as the only element. Singleton array. Very simple. So this stuff is easy. This stuff a bit more complex. I had said about list of strings, right? List strings. But the string part is polymorphic. There might be other types, and if it happens, there are other types. This stuff will still continue. Thing is, the problem is, return and join have, in this case, are specific to list endofunctor. For example, if you try to say how to return, how to get this unit element on the identity endofunctor, it will be a bit different, right? Because we will not get an array of stuff. It will be different for each endofunctor. So if we somehow define this join and return on each endofunctor, we will inject the monoid part to each endofunctor at that point. So each endofunctor will have this extension, this monoidic part, and essentially will become monad. The endofunctors that will have join and return of these types, or similar types, will give us the monads. So join and return from the monad with endofunctors being containers and preserving arrows is a monad. That's it. Questions?
Ну, все понятно. Какие еще примеры интересные, кроме листа, можно придумать?
Все что угодно.
Ну, с maybe, например, что?
Сейчас, если я смогу сделать.
JavaScript Promise, да?
Ну, з maybe, наприклад, може бути, ти хочеш взяти з ліста head, ну, в тебе приходить empty list. І ти кажеш, що в тебе або прийде, наприклад, string, якщо в тебе є string, або в тебе у нас, тому що в тебе empty list.
Maybe, если это будет так, то на первом уровне мы смотрим, что в первом уровне maybe есть что-то. Если есть, то идем дальше, на втором уровне. Двойной уровень pattern matching. Если нет на первом уровне, то мы сразу возвращаем на. И таким образом из maybe string мы получим просто maybe string. И это будет join на maybe. Return на maybe это будет просто just something. Это просто. А identity будет очень просто. Потому что identity string, значит, что типа на первом уровне нужно идти еще чуть-чуть глубже и взять просто там из нижней колонки. Для, допустим, error. Для error нам нужно будет на первом уровне посмотреть, была ли ошибка. Если ее не было, то пойти дальше и посмотреть, была ли ошибка внутри. Если там ее не было, то возвращать значение. Если была ошибка на первом уровне, то возвращается ошибку с первого уровня. То же самое, как maybe, только чуть-чуть иначе. Проблема в том, что join и return мы не можем сделать generic. Мы не можем их сделать такими, чтобы они были на всех endofunctors. Поэтому только те endofunctors, у которых есть join и return, для которых мы это определили, становятся монадами. Монады — это endofunctors, у которых есть вот эти две функции. И эти две функции на самом деле дают очень крутую штуку. Они позволяют нам сделать композицию endofunctors, даже тех, у которых это полиморфичные типы отличаются. Поэтому на самом деле вся прелесть мало. Монады сами по себе ничего себе не представляют. То, что интересно на самом деле в монадах, это endofunctors. И это то, что, наверное, очень многие упускают. Вот. Еще вопросы?
Люди продолжают переваривать.
Все, спасибо.